computer architecture, floating point. Let's continue where we left the lecture last lecture. We said that we could represent the number in scientific notation, 3.28 times 10 to the power 21. Then we can float this point, that's why it's called floating point, to within the what we call the fraction, and then we adjust simultaneously, we adjust the exponent. Now what is happening then is that we have some freedom of choosing the exponent and freedom of choosing the fraction. By the way, just a small stop in between, we can also write this number in what we call the engineering notation. So that is the same, but instead of, for instance, writing 10 to the power 21, we write E21, which means 10 to the power 21, but this can be written in ASCII, and as you know, on your computer it's very difficult to write this exponent, so this E21 is very easy to write. So when you write a program, then you normally use the engineering notation, but here for the reasoning I will just use the scientific notation with a fraction times 10 to the power and an exponent. And we've done it like this. We floated the point to such a way that we have no more digits unequal to 0 after the floating point. So now we can remove the part after the floating point, and we just have an integer here and an integer there. So we could use them for our computers, because computers work only with integers, because it's a finite state machine. Now let's do an example. So let's take 5 digits in total on the computer, but everything is decimal for the moment. It's decimal. Later we will do in binary, but for the moment let's take a decimal computer, and it has 3 digits here for the fraction, and it has 2 digits here for the exponent, or exponent, I don't know actually, I will call it exponent. So what is actually then the range of numbers that we can get? Let's take a look at it. The smallest number we will get, and it also has signs for both in front of the fraction and in front of the exponent, I must say, before we continue. So the smallest number, as you can imagine, is minus 999 times 10 to the power 99. And the largest positive number is plus 999 10 to the power 99. But that is quite obvious. But what is the smallest negative number and smallest positive number? These are minus 001 times 10 to the power minus 99 and 001 times 10 to the power minus 99 plus 011. And all the other numbers, so if these digits are 000 plus or minus, it doesn't matter, then as long as these 3 digits are 0, the exponent doesn't matter anymore, because they are all 0. So we have quite a lot, let's say 1,000, we have about 100 zeros then to our disposition. So let's put this in a picture. So we have here the smallest negative number, the biggest negative number, the smallest positive number, and the biggest positive number. Now everything that goes in this range, it's not accessible to our computation because it's too big. We call this overflow. The same on the other side for negative numbers, we call this overflow. So if an overflow error occurs in your calculation, it happens because the number is simply too big to fit in the 5 digits. And here we have, and this normally causes the program to crash or something like this, or your calculator that you have, your pocket calculator, it will give some error. On the other side we have the smallest negative number and the smallest positive numbers, as we've seen here before. We have these values in engineering notation. Now what happens if we go into this what we call underflow region? That is no problem whatsoever for your calculator, or for your computer. They will just set it to 0 and the program continues. So we have here, let's say, 7 regions in numbers scale. Overflow, good calculations; underflow, 0, here normal calculations, and overflow. Now what we could do, of course, we could have, for the 5 digits, we choose in here 3 for the fraction and 2 for the exponent. We could do the things like, let's put 4 for the fraction and only 1 for the exponent. So what will happen then? Well, let's first say that we have to say that the error in our calculations, they are about 1 compared to 999. So we have here the error of this number that we have here. The relative error is about 1,000th, because we have plus or minus 1. That is we call it digitalization error of the number, the rounding error. It rounds up to the nearest integer. And then relatively to the total number, this will be 1 divided by 1,000. And what now if we make 4 of those digits in front and 1 digit for the exponent? So now the smallest number is 99999 times 10 to the power only 9, and the others, well, I will believe when I say this, we have also a lot of zeros. Again, we have the biggest positive number is actually it's smaller than the other one, because this one is actually smaller than the biggest number we had here. The largest positive number was 999, so that is 1000 times 10 to the power 99, so that is 10 to the power 102 approximately, while in this case it is 10 to the power 4, 10,000 times 10 to the power 9, that is 10 to the power 13. So the largest number is much smaller, but on the other hand, so we have a smaller range of our computations, but on the other hand, the relative error is now, again, it's plus or minus 1, this last digit, that is our rounding error, but that is now relatively is much smaller, it's only 1 divided by 10,000. So now we have, if we have 5 digits space in our computer for doing calculations, we can decide for an architecture that is using 4 digits for the fraction, 1 digit for the exponent, and or we can do, for instance, 3 digits for the fraction and 2 digits for the exponent. So then we have to choose, what do we want? Do we want high precision in our calculations, or do we want a large range for our calculations? So we have to decide what we have to do, one or the other, range or precision.